Good day, BS Ed Mathematics 2-2. How's your week so far? Again, welcome to the class Elementary Statistics and Probability. Last week, our teacher discussed the probability and counting rules. In this video, we, the group 3, we're going to tackle the discrete probability distributions. Many decisions in business, insurance, and other real-life situations are made by assigning probabilities to all possible outcomes pertaining to the situation and then evaluating the results. For example, a saleswoman can compute the probability that she will make sales in a single day. An insurance company might be able to assign probabilities to the number of vehicles a family owns. A self-employed speaker might be able to compute the probabilities for giving speeches each week. Once these probabilities are assigned, statistics such as the mean, variance, and standard deviation can be computed for this event. With these statistics, various decisions can be made. In this video, we are going to explain the concepts and application of what is called a probability distribution. What is probability distribution? Before we are going to discuss what is probability distribution is all about, let's first recall the definition of the words or phrases that we need to understand before we are going to dig deeper to what is probability distribution is all about. First thing that we need to recall is variable. So, a variable was defined as a characteristic or attribute that can assume different values. Various letters of the alphabet such as the X, Y, or Z are used to represent variables. That's the very common thing that we have encountered several times already. Since the variables that we are going to talk in this video are associated with probability, they are called random variables. For example, if a die is rolled, a letter such as X can be used to represent the outcomes. Then the values that X can assume is 1, 2, 3, 4, 5, or 6, or corresponding to the outcomes of rolling a single die. Another example, if 2 coins are tossed, a letter, let's say Y, can be used to represent the number of heads. In this case, 0, 1, or 2. As another example, if the temperature at 8 a.m. is 43 degrees Celsius and at noon it is 53 degrees Celsius, then the values T that the temperature assumes are said to be random, since they are due to various atmospheric conditions at the time the temperature was taken. So, in other words, a random variable is a variable whose values are determined by chance. Another definition that we need to recall is the discrete variable. So, what is discrete variable, everyone? When we say discrete variable, it means that a variable can assume only a specific number of values, such as the outcome for the roll of a die or the outcomes for the toss of a coin. Discrete variables have a finite number of possible values or an infinite number of values that can be counted. The word counted means that they can be enumerated using the numbers 1, 2, 3, etc. For example, in the number of joggers in the Riverview Park each day and the number of phone calls received after a TV commercial airs are example of discrete variables since they can be counted. So in this video, we are going to focus on discrete random variables. So what is discrete probability distribution? But before we are going to define that, let me give you an example first. Let's say a probability distribution for a discrete random variable uses the probability experiment of tossing 3 coins. So the sample space will be TTT, TTH, THT, HTT, HHT, HTH, THH, and HHH. If X is represented by the random variable for the number of heads, then X assumes the value 0, 1, 2, or 3. Probabilities for the value of X can be determined as follows. As you can see on the screen, it was being separated with no heads, 1 head, and 2 heads. The sample space were also being put in its own place. The total number of sample space is 8. That's why its denominator is 8, as you can see. Therefore, the probability of getting no heads is 1/8, one head is 3/8, two heads is 3/8, and three heads is 1/8. For these values, a probability distribution can be constructed by listing the outcomes and assigning the probability of each outcome, as shown here. Since we represented x as the number of heads, the value of it is 0, 1, 2, and 3, and it was shown in a table the probability of getting heads in a sample space. Therefore, a discrete probability distribution consists of the values a random variable can assume the corresponding probabilities of the values. The probabilities are determined theoretically or by observation. Discrete probability distributions can be shown by using a graph or a table. Probability distributions can also be represented by a formula. For example, construct a probability distribution for rolling a single die. So, the solution for it is, since the sample space is 1, 2, 3, 4, 5, and 6, and it was represented by the outcome x, and each outcome has a probability of 1/6, the distribution is as shown at the screen. Probability distributions can be shown graphically by representing the values of x on the x-axis and the probabilities p of x and the y-axis. Let's go back to the first example that I gave, which is probability distribution for the sample space for tossing 3 coins. We must represent these probability distributions in a graphical manner. As you can see on the screen, this will be the result or the representation of the graph. The values that x assumes are located on the x-axis, and the values of p of x are located on the y-axis. Note that for visual appearances, it is not necessary to start with 0 at the origin, as you can see on the x-axis. Since the 0 represented the no heads on the outcome, thus it will be graphed like that. The same follows on the other outcomes. The examples that I gave, which are rolling a die and tossing 3 coins, are illustrations of theoretical probability distributions. In theoretical probability distributions, you do not need to actually perform the experiments to compute the probabilities. In contrast, empirical probability distributions need to construct actual probability distributions, and you must observe the variable over a period of time. Let me give you an example of empirical probability distribution. For example, the Baseball World Series is played by the winner of the National League and the American League. The first team to win 4 games wins the World Series. In other words, this series will consist of 4 to 7 games, depending on an individual victories. The data shown consists of the number of games and played in the World Series from 1965 through 2005. There was no World Series in 1994. The number of games played is represented by the variable x. Find the probability p of x for each x, construct a probability distribution, and draw a graph for data. The solution. The probability p of x can be computed for each x by dividing the number of games x by the total. For 4 games, it will be 8/40 is equals to 1/5 or 0.2. For 5 games, it will be 7/40 is equals to 0.175. For 6 games, it will be 9/40 is equals to 0.225. And for 7 games, it will be 16/40 is equals to 2/5 or 0.4. The probability distribution is in a table form shown at my side. The graph will look like this. X-axis represents the number of games and the y-axis will be the probability. There are 2 requirements for a probability distribution you must remember. Number 1, the sum of the probabilities of all the events in the sample space must equal to 1. That is, summation of the probability of x is equal to 1. And number 2, the probability of each event in the sample space must be between or equal to 0 and 1. That is, 0 is greater than or equal to p of x is less than or equal to 1. The first requirement states that the sum of the probabilities of all the events must be equal to 1. This sum cannot be lesser than 1 or greater than 1 since the sample space includes all the possible outcomes of the probability experiment. The second requirement states that the probability of any individual event must be a value from 0 to 1. The reason is that the range of the probability of any individual value can be 0, 1, or any value between 0 and 1. A probability cannot be a negative number or greater than 1. Let me give you an example for a better understanding of the two requirements for a probability distribution. Determine whether each distribution is a probability distribution. For A, is it a probability distribution or not? The answer will be yes, it is a probability distribution since the sample space is equal to 1 and the p of x is lesser than 1 but greater than 0. For B, is it a probability distribution or not? The answer will be no, it is not a probability distribution since the p of x cannot be 1.5 or negative 1.0. Thus, it violates the two requirements for a probability distribution. For C, is it a probability distribution or not? The answer will be yes, it is a probability distribution since it abides the two requirements. And lastly, for D, is it a probability distribution or not? The answer will be no, it is not since the summation of p of x is equal to 1.2. That would be all. My name is Dayan Jane T. Clarabelle. The other lessons will be discussed by my other teams. Thank you and have a nice day.
Good day everyone. So my assigned topic is all about the mean, variance, standard deviation, and expectation and the probability distribution. Before we proceed to the lesson proper, let me present to you the objective. So at the end of the lesson, students are expected to find the mean, variance, standard deviation, and expected value for a discrete random variable. Mean. To find the mean of a probability distribution, you must multiply each possible outcome by its corresponding probability and find the sum of the products. So here is the formula for the mean of a probability distribution. Mu is equals to x sub 1 times p of x sub 1 plus x sub 2 times p of x sub 2 plus x sub 3 times p of x sub 3 and so on and so forth. So that is equals to the summation of x times p of x, where x sub 1, x sub 2, x sub 3 are the possible outcomes and p of x sub 1, p of x sub 2, p of x sub 3 are the probability. Note that the summation of x times p of x means to sum the products. So ang x ana nga sa formula is the possible outcome and the p of x is the probability. So, rounding rule for the mean, variance, standard deviation for a probability distribution. The rounding rule for the mean, variance, and standard deviation for variables of a probability distribution is this. The mean, variance, and standard deviation should be rounded to one more decimal place than the outcome x. So when fractions are used, they should be reduced to lowest term. So for example, rolling a die. Find the mean of the number of spots that appear when a die is tossed. So, in the toss of a die, the mean can be computed. Thus, the outcome x will be 1, 2, 3, 4, 5, 6 since uno man ka spot ang mo appear sa die. And then ang probability nga maka spot of number 1 is 1 over 6. So pareha na sila tanan nga 1 over 6 ang probability since kada rule sa die usara man jud ka spot ang mo appear. So let us find the mean of ruling a die. So ang formula is mean is equals to summation of x times p of x. So first atong buhaton, atong i-multiply ang outcome sa corresponding nga probability. So, outcome number 1, ang probability is 1 over 6. So, ato nang i-multiply. 1 times 1 over 6 plus 2 times over 6 plus 3 times 1, 6 plus 4 times 1, 6 plus 5 times 1, 6 plus 6 times 1, 6. So, the total is 21 over 6. So, ato man ang i-reduce into lowest term. That is equals to 3 and 1/2. So, ato ba ito na itong himuong decimal? That is equals to 3.5. So, let's have another example in getting mean. Children in a family. In a family with 2 children, find the mean of the number of children who will be girls. So, ang atong outcome, possible outcome, or the number of girls will be 0, 1, and 2. And then atong corresponding probability, sa 0 is equals to 1/4, sa 1 is equals to 1/2, and then 2 is equals to 1/4. So, hence, the mean is the summation of x times p of x. So, ang atong buhaton is, atong i-multiply ang outcome sa kada probability. And then, isum up. So, first is 0 times 1/4 plus 1 times 1/2 plus 2 times 1/4. So, that is equals to 1. So, ang atong mean is 1. Now, let's move on to variance and standard deviation of a probability distribution. So, we can find the variance of a probability distribution by multiplying the square of each outcome by its corresponding probability. And then, summing those products and subtracting the square of the mean. So, the formula for the variance of a probability distribution is lowercase sigma squared equals summation of bracket x squared times p of x bracket minus mean squared. And also, formula sa standard deviation is pare-pareho ra sa variance but atong square root ang variance. So, mao na ang standard deviation formula. So, now, let us have an example in getting variance and standard deviation. So, compute the variance and standard deviation and a probability distribution in example 5.5. So, recall that the mean is 3.5 as computed in example 5.5. So, now, kuha na to ang variance. So, ang pagkuha sa variance is the summation of x squared times p of x bracket minus mean squared. So, first, atong buhaton is squared na to ang every outcome and then i-multiply sa corresponding probability. So, first is 1 squared times 1/6 plus 2 squared times 1/6 plus 3 squared times 1/6 plus 4 squared times 1/6 and so on. Andun nga moabot sa ika-6 nga outcome, the same process. And then, atong isum up. Tanan. ang total adto minusa nato sa mean, which is 3.5 squared. So atong squared una ang mean, usa i-minus sa na-compute nato nga x squared times p of x, summation sa x squared times p of x. So that is equals to 2.9. So naana tay variance nga 2.9. So ang pagkuha sa standard deviation is simply the square root of variance. So naaman tay 2.9 nga variance. So square root na to ang 2.9. So the answer is 1.7. So ang atong variance is 2.9. Ang atong standard deviation is 1.7. Let's have another example. A box contains 5 balls, 2 numbered 3, 1 is numbered 4, and 2 are numbered 5. The balls are mixed and 1 is selected at random. After a ball is selected, its number is recorded. Then it is replaced. If the experiment is repeated many times, find the variance and standard deviation of the numbers on the balls. So, the probability distribution is number of ball, possible outcome is 3, 4, 5. So, mo ni ang mga numbers sa balls. So, ang probability, corresponding probabilities is sa number 3 nga ball, 2/5 ang probability. Sa number 4, 1/5. Sa number 5, 2/5. So, first na itong buhaton is, kuhaon na to ang mean. So, the formula of mean is summation of x times p of x. So, 3 times 2/5 plus 4 times 1/5 plus 5 times 2/5 equals 4. So, 4 is ang ato ang mean. Now, kuhaon na to ang variance. So, ang variance is summation of x squared times p of x bracket minus m squared. So, 3 squared times 2/5 plus 4 squared times 1/5 plus 5 squared times 2/5. So, that is equals to 16 4/5. Now, minusan na to sa mean squared. So, ang mean is 4. So, atong squared ang 4, that is equals to 16. Ato ang i-minus sa 16 4/5. So, 16 4/5 minus 16 is equals to 4/5. So, mauna ang atong variance. Now, kuhaon na to ang standard deviation. Standard deviation is denoted by the square root of variance. So, square root of 4/5 is equals to, atong decimal ang 4/5 is square root of 0.8. So, that is equals to 0.894. So, mauna ato ang standard deviation. So, the mean, variance, and standard deviation can also be found by using vertical columns as shown. So, pwede sa nato gamitang vertical columns aron madali ang pagkuha sa mean, variance, and standard deviation. So, ang atong possible outcome, which is 3, 4, 5. And then, p of x corresponding probability. Sa number 3 is 2/5. So, himo na itong decimal. Atong mahimo na siyang 0.4. Sa 4, which is 1/5, mahimo na siyang 0.2. Sa 5, which is 2/5, mahimo siyang 0.4. And then, x times p of x. So, ato siyang i-times. So, 3 times 0.4 is equals to 1.2. 4 times 0.2 is equals to 0.8. And then, 5 times 0.4 is equals to 2.0. So, aron makuha na to ang mean, atong isum up ang answer sa x times p of x sa kada outcome. So, 1.2 plus 0.8 plus 2.0 is equals to 4.0. So, ang atong mean is 4.0. Sunod, natong buhaton is x squared times p of x. X squared, so 3 times 3 which is 9 times p of x which is 0.4, that is equals to 3.6. Next, x squared times p of x, so 4 times 4 which is 16 times p of x 0.2, that is equals to 3.2 and so on. So, ang atong x squared times p of x is equals to 16.8. So now, nahuman na to ang compute ang vertical columns. So nakuhaon na to ang variance and standard deviation. So we can find the mean by summing x times p of x. So mao na to ang atong mean, which is 4. Find the variance by summing the x squared times p of x column and subtracting the square of the mean. So, kwaon na to ang variance. So, 16.8 mao man na ang nasa formula is summation of x squared times p of x. Ato naman ang total, which is 16.8 minusan na to sa squared sa mean, which is 4. So, 16.8 minus 4 squared equals 16.8 minus 16 equals to 0.8. So, pag nanatay, variance nga 0.8. So, atong kwaon is standard deviation. Standard deviation can be denoted by the square root of the variance. So, square root sa 0.8 is equals to 0.894. So, the same rag answer sa vertical columns o katong atong gihimo pag una. Expectation. Another concept related to the mean for a probability distribution is that of expected value or expectation. Expected value is used in various types of games of chance, in insurance, and in other areas such as decision theory. The expected value of a discrete random variable of a probability distribution is the theoretical average of the variable. So the formula is mu is equals to e of x is equals to summation of x times p of x. So pareha na siya formula sa mean. The symbol e of x is used for the expected value.
When expected value problems involve money, it is customary to round the answer to the nearest cent. So let's have an example. 1,000 tickets are sold at $1 each for a colored television valued at $350. What is the expected value of the gain if you purchase one ticket? So mao ni ang solutions. Ang gain, which is Rx, so na ay win or lose. So ang win, kung mudaog ka, maka-gain ka og $349. So nganong $349 man instead of $350? So of course, nipalit man ka og isa ka ticket. So kung mudaog ka, equivalent na og $349 kay dili naman mabalik to ang imong gipalit sa ticket. So sa lose, so negative $1. So nganong negative $1 man? Kay syempre mawad-an jud ka og $1 kay nipalit man ka og ticket that worth $1. So sa probability, sa win, ang imong probability is 1 over 1,000. Kay sa 1,000 ka ticket, usara man ka ticket imong gipalit. So 1 over 1,000 ra ang chances of winning. So sa loss nimo is 999 over 1,000 kay mas daghan ka og chances of nga mapildi kay usara man ka ticket ang imong gipalit. So mao na 999 over 1,000. Two things should be noted. First, for a win, the net gain is $349 since you do not get the cost of the ticket, which is $1 back. So second, for a loss, the gain is represented by a negative number. So in this case, negative $1. So let's get the expected value of the winning tickets. So E of x is equals to the summation of x times P of x. So ang atong x is ang gain. So let's have $349 times 1 over 1,000 plus negative $1 times 999 over 1,000. So that is equals to negative $0.65. Expected value problems of this type can also be solved by finding the overall gain. The value of the prize won or the amount of money won, not considering the cost of the ticket for the prize or the cost to play the game as shown. So, pwede sad kani atong himuon nga formula in getting expected value. So, E of x is equals to overall gain is $350 times the probability 1 over 1,000 minus the cost of the ticket, which is $1. So that is also equals to negative $0.65. So note that the expectation is negative $0.65. This does not mean that you lose negative $0.65 since you can only win a television set valued at $350 or lose at $1 on the ticket. What expectation means is that the average of the losses is 0.65 for each of the 1,000 ticket holders. So that was the end of my topic. Thank you everyone for watching.
Good day everyone. Hello, kumusta tang tanan? I hope everyone is doing well, no? I am the next reporter after Miss Emily Kwamag. My name is Kisha Kid Blas and I'm going to report the third topic in discrete probability distributions, which is the binomial distribution. But before we get into my discussion, let's play a game, So, are you guys ready? So, our game is something we are all familiar with already. It is the jumble letters. So a jumble letter game is a word game, no? Word games are essentially some special brain teasers or unscrambled words that test our language skills. It may help us expand our vocabulary, improve our word recall, and improve our working memory. So in this part, there will be random letters on the screen. You have to arrange those letters to be a correct word that relates to my discussion, the binomial distribution. So I'm requesting everyone to cooperate, no? This is only 4 jumbled letters. Please list your answers and write it on my post in the class comments. Every jumbled word will have a time limit of 5 seconds. So, are you all ready? Let us start. Number 1. And the correct answer is, okay, it's binomial experiment number 2. And the correct answer is 2 outcomes, number 3. And the correct answer is binomial distribution. And for the last one, number 4. And the correct answer is binomial probability formula. In summarization of our answers, the words are binomial experiment, 2 outcomes, binomial distribution, and binomial probability formula. So according to these words, I believe everyone have already an idea or glimpse on what my topic is mostly about. But before proceeding to the discussion proper, let me read the following objectives. First, describe what is binomial experiment. Second, identify the 4 requirements that satisfy the binomial experiment. Third, identify the notation for the binomial distribution. Fourth, find the exact probability for x successes in n trials of a binomial experiment. And lastly, number 5, find the mean, variance, and standard deviation for the variable of a binomial distribution. Many types of probability problems have only two outcomes or can be reduced to two outcomes. For example, when a coin is tossed, it can be heads or tails. When a baby is born, it will be either male or female. In a basketball game, a team either wins or loses. A true or false item can be answered in only two ways, true or false. Other situations can be reduced to two outcomes. For example, a medical treatment can be classified as effective or ineffective depending on the results. A person can be classified as having normal or abnormal blood pressure depending on the measure of the blood pressure gauge. A multiple choice question, even though there are 4 or 5 answer choices, can be classified as correct or incorrect. Situations like these are called binomial experiments. A binomial experiment is a probability experiment that satisfies the following 4 requirements. Number 1. There must be a fixed number of trials. This should go without saying if you don't have a fixed number of trials. For example, you could be tossing a coin forever without stopping. In addition, the results from our experiment will be vastly different if we toss that coin twice or if we toss it 100 times. The number n can be any amount. For example, if we flip a coin 100 times, then n is 100. Number 2. Each trial can have only 2 outcomes or outcomes that can be reduced to 2 outcomes. These outcomes can be considered as either success or failure. In other words, if you can phrase the experiment as a yes or no answer, then it can be a binomial experiment. For example, will I get a heads? Can someone find a parking space in the city? We often call outcomes either a success or a failure, but a success is just a label for something we are counting. For example, when we flip a coin, we might call a head a success and a tail a failure. Number 3. The outcomes of each trial must be independent of one another. This simply means that the outcomes of one trial does not affect the outcomes of another trial. For example, suppose we flip a coin and it lands on heads. The fact that it landed on head does not change the probability that it will land on heads in the next flip. Number 4. The probability of a success must remain the same for each trial. In order for an experiment to be a true binomial experiment, the probability of success must be the same for each trial. For example, when we flip a coin, the probability of getting heads or success is always the same each time we flip the coin. Example of a binomial experiment. Roll a fair 6-sided die 20 times. Record the number of times that a 2 comes up. First, the experiment consists of n repeated trials. In this case, there are 20 trials. Okay. Number 2, each trial has only 2 possible outcomes. If we define a 2 as a success, then each time the die either land on a 2 a success or some other number a failure. Number 3, each trial is independent. The outcome of one die does not affect the outcome of any other die row. Number 4, the probability of success is the same for each trial. For each trial, the probability that the die lands on a 2 is 1 over 6. This probability does not change from one trial to the next. Not an example of binomial experiment. Ask 100 people how old they are. Why is this not an example of binomial experiment? This is not a binomial experiment because there are more than 2 possible outcomes. Next, roll a fair 6-sided die until a 5 comes up. Why is this not an example of binomial experiment? This is not an example of binomial experiment because there is not a predefined n number of trials. We have no idea how many rolls it will take until a 5 comes up. A binomial experiment and its results give rise to a special probability distribution called the binomial distribution. The outcomes of a binomial experiment and the corresponding probabilities of these outcomes are called a binomial distribution. In binomial experiment, the outcomes are usually classified as success or failures. For example, the correct answer to a multiple choice item can be classified as a success, but any of the other choices would be incorrect and hence classified as a failure. The notation that is commonly used for binomial experiments and the binomial distribution is defined as P open parentheses S close parentheses is the symbol for the probability of success. P open parentheses F close parentheses is the symbol for the probability of failure. The small letter p is the numerical probability of success. The small letter q is the numerical probability of a failure. So the symbol for the probability of success is equals to the numerical probability of success. And the symbol for the probability of failure is equals to 1 minus the numerical probability of success is equals to the numerical probability of a failure. The small letter n is the number of trials. The big letter x is the number of successes in n trials. Note that 0 is less than or equal to x and x is less than or equals to n. And x is 0, 1, 2, 3, and so on. The probability of success in a binomial experiment can be computed with this formula. Binomial probability formula. In a binomial experiment, the probability of exactly x successes in n trials is p open parentheses x close parentheses is equals to n factorial divided by open parentheses n minus x close parentheses factorial x factorial multiplied by p to the power of x multiplied by q to the power of n minus x. For an example, a coin is tossed 3 times. Find the probability of getting exactly 2 heads. So I will ask, is this situation an example of a binomial experiment? Yes or no? So from the standpoint of a binomial experiment, one can show that this situation meets the 4 requirements. So this situation is a binomial experiment. How? Number 1, there are a fixed number of trials. There is 3. Number 2, there are only 2 outcomes for each trial, heads or tails. Number 3, the outcomes are independent of one another because the outcome of one toss in no way affects the outcome of another toss. And lastly, the probability of success or heads is in each case. So this is a binomial experiment. Okay, the solution of this experiment. This problem can be solved by looking at the sample space. So our sample space are head, 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 tail, head, tail, head, tail, head, head, tail, tail, head, tail, head, tail, head, tail, 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 tail. So from this sample space, we can conclude that there are 3 ways to get 2 heads. So our answer is 3/8, or in decimal form, 0.375. Okay, let's try answering by using the binomial probability formula. In this case, the n is 3, the x is 2, the p is 1/2, and the q is 1/2. Hence, substituting in the formula, we will arrive still at the same answer from the sample space. Our answer would still be together as 3/8 or 0.375. Computing probabilities by using the binomial probability formula can be quite tedious at times, no? So tables have been developed for selected values of n and p. The table gives the probabilities for individual events. This shows how to use the table to compute probabilities for binomial experiments. So from the table now, we can find the n 3, the x 2, and the p 0.5. So the value is 0.375. And to those who are wondering, this yung gikan ng table, ma'am, yung sa paggama ng table with the given values. Well, to answer your question, from my research, I found out that this table is from the binomial table, Monchi class. Binomial table. Number in the table represent p x equals to x for a binomial distribution with n trials and probability of success p. So, taas pa ni siya, no, na apay more numbers sa n and x. Okay, next example. Survey on doctor visits. A survey found that 1 out of 5 Americans say he or she has visited a doctor in any given month. If 10 people are selected at random, find the probability that exactly 3 will have visited a doctor last month. So, our solution. Let us substitute n 10, p 1/5, x3, and q 4/5. So, substituting in the formula, we will arrive with the answer decimal 0.201. Okay, I hope everyone understands my discussion so far, no? So let us move on to my next topic, the mean, variance, and standard deviation for the binomial distribution. The mean, variance, and standard deviation of a variable that has a binomial distribution can be found by using the following formulas. For the mean, it is equals to n multiplied by p. Variance is equals to n multiplied by p multiplied by q. Standard deviation is equals to the square root of n multiplied by p multiplied by q, where our n is the number of fixed trials, our p is the probability of success in one of the n trials, and q is the probability of failure in one of the n trials. Example, a die is rolled 480 times. Find the mean, variance, and standard deviation of the number of 3s that will be rolled. So from this example, is this an example of a binomial experiment? Is it a yes or no? So I believe this is a binomial experiment. Why? This is a binomial experiment since getting a 3 is a success and not getting a 3 is considered a failure. So let us substitute in the formula where our n is 480, our p is 1 over 6, and our q is 5 over 6. So our mean would be 80, our variance would be 66.67, and our standard deviation is 8.16. Next example, the statistical bulletin published by Metropolitan Life Insurance Corporation reported that 2% of all American births result in twins. If a random sample of 8,000 births is taken, find the mean, variance, and standard deviation of the number of births that would result in twins. So from this example or situation, do you think this is an example of binomial experiment? Is it a yes or no? So I believe this is still a binomial experiment. Why? This is a binomial experiment since a birth can result in either twins or not twins. Okay, so from the given example, let us substitute the given n, 8,000. P is equals to 0.02. Q is 0.98. And to those who are wondering where we get the P and Q, so P is from the 2% and the remaining 98% is in Q, which is 0.98. So substituting, we would get our mean of 160, our variance of 156.8, and our standard deviation of 12.5. So that is all for my discussion, class. But before I end, I have here an assessment. Answer whether the following is a binomial experiment or not. This is only 2 situations. The same method with my intro game, I will give 5 seconds, and please leave your answers in our class comments for me also to know that you listen and understand my discussion. Okay, number 1. Telephone surveying a group of 200 people to ask if they voted for Juan de la Cruz. Your 5 seconds starts now. Time's up. So is this a binomial experiment or not? Well, it is. Why? So step 1, ask yourself, is there a fixed number of trials? The answer is yes, which is 200. Step 2, ask yourself, are there only 2 possible outcomes? For this situation, the only possible outcomes are that they did or they did not vote for Mr. Juan de la Cruz. So the answer is yes. Step 3, ask yourself, are the outcomes independent of each other? The answer is yes. One person saying they did or they did not vote for Mr. Juan de la Cruz is not going to affect the next person's response. Step 4, does the probability of success remain the same for each trial? The answer is yes. Each person has a 50% chance of having voted for Mr. Juan de la Cruz. So we can conclude that this first situation is a binomial experiment. Okay, number 2. Our next and last situation. You take a survey of 50 traffic lights in a certain city at 3 p.m., recording whether the light was red, green, or yellow at that time. Okay, your 5 seconds starts now. Time's up. Okay, so is this a binomial experiment or not? Well, it is not. Why? Step 1. Ask yourself, is there a fixed number of trials? Well, the answer is yes. There's a fixed number of trials, which is the 50 traffic lights. But in step 2, ask yourself, are there only 2 possible outcomes? No, there are 3 possibilities, the red, green, and yellow. So we can conclude that this situation number 2 is not a binomial experiment. Okay, so this ends my discussion for today. I hope everyone learns a lot about the third topic in the discrete probability distributions. Thank you for watching, and I will leave a quote from Walter Bagehot. Life is a school of probability. Thank you everyone, and please welcome our last reporter, Ms. Lancy Silidio.
Good day, class. The concepts of my discussion is all about the other types of distribution. Before we start our lesson proper, let's have first our learning objectives. So at the end of this lesson, you will be able to describe and provide examples of the other types of distributions, compute probabilities using the Poisson, hypergeometric, and multinomial probability formula. And lastly, find the probabilities for outcomes of variables using the Poisson, hypergeometric, and multinomial distribution.
The multinomial distribution. Recall that in order for an experiment to be binomial, 2 outcomes are required for each trial. But if each trial in an experiment has more than 2 outcomes, a distribution called the multinomial distribution must be used. For example, a survey might require 2 responses of approve, disapprove, or no opinion. In another situation, a person may have a choice of one of 5 activities for Friday night, such as a movie, dinner, baseball game, play, or party. Since these situations have more than 2 possible outcomes for each trial, the binomial distribution cannot be used to compute probabilities. The multinomial distribution can be used for such situations if the probabilities for each trial remain constant and the outcomes are independent for a fixed number of trials. The events must also be mutually exclusive. Note that the formula for the multinomial distribution, if x consists of events e sub 1, e sub 2, e sub 3, and so on, e sub k, which have corresponding probabilities p sub 1, p sub 2, p sub 3, and so on, p sub k, of occurring, and x sub 1 is the number of times e sub 1 will occur, and x sub 2 is the number of times e sub 2 will occur, and x sub 3 is the number of times e sub 3 will occur, and etc. Then the probability that x will occur is equal to n factorial over x sub 1 factorial times x sub 2 factorial times x sub 3 factorial and so on, x sub k factorial times p sub 1 to the power of x sub 1 times p sub 2 to the power of x sub 2 and so on, p sub k to the power of x sub k, where x sub 1 plus x sub 2 plus x sub 3 and so on plus x sub k is equal to n and p sub 1 plus p sub 2 plus p sub 3 and so on to p sub k is equal to 1. Example of a multinomial distribution is the leisure activities. In a large city, 50% of the people choose a movie, 30% choose dinner and a play, and 20% choose shopping as a leisure activity. If a sample of 5 people is randomly selected, find the probability that 3 are planning to go to a movie, 1 to a play, and 1 to a shopping mall. To solve this one, we know that n is equal to 5, x sub 1 is equal to 3, x sub 2 is equal to 1, x sub 3 is equal to 1, and p sub 1 is equal to 0.50, p sub 2 is equal to 0.30 and P sub 3 is equal to 0.20. Substituting in the formula, it gives probability of x is equal to 5 factorial is 5 Substituting in the formula, it gives probability of x is equal to 5 factorial over 3 factorial times 1 factorial times 1 factorial times 0.50 to the power of 3 times 0.30 to the power of 1, 0.20 to the power of 1 is equal to 0.15. Again, note that the multinomial distribution can be used even though replacement is not done, provided that the sample is small in comparison with the population. Another example is the CD purchases. In a music store, a manager found that the probabilities that a person buys 0, 1, or 2 or more CDs are 0.3, 0.6, and 0.1 respectively. If 6 customers enter the store, find the probability that 1 won't buy any CDs, 3 will buy 1 CD, and 2 will buy 2 or more CDs. To solve this problem, it is given that n is equal to 6, x sub 1 is equal to 1, x sub 2 is equal to 3, x sub 3 is equal to 2, and p sub 1 is equal to 0.3, p sub 2 is equal to 0.6, and p sub 3 is equal to 0.1. Then, probability of x is equal to 6 factorial over 1 factorial times 3 factorial times 2 factorial times 0.3 to the power of 1 times 0.6 to the power of 3 times 0.1 to the power of 2. Then equals to 60 times 0.3 times 0.216 times 0.01 is equal to 0.03888. So that is the answer for finding the probability that 1 won't buy CDs, 3 will buy 1 CD, and 2 will buy 2 or more CDs. So next is example is the selecting colored balls. A box contains 4 white balls, 3 red balls, and 3 blue balls. A ball is selected at random, and its color is written down. It is replaced each time. Find the probability that if 5 balls are selected, 2 are white, 2 are red, and 1 is blue. To solve this problem, we know that n is equal to 5, x sub 1 is equal to 2, x sub 2 is equal to 2, x sub 3 is equal to 1, and p sub 1 is equal to 4 over 10, p sub 2 is equal to 3 over 10, and p sub 3 is equal to 3 over 10. Hence, probability of x is equal to 5 factorial hence, the probability of x is equal to 5 factorial over 2 factorial times 2 factorial times 1 factorial times 4 over 10 to the power of 2 times 3 over 10 to the power of 2 times 3 over 10 to the power of 1 is equal to 81 over 625. That is the answer. Thus, the multinomial distribution is similar to the binomial distribution but has the advantage of allowing you to compute probabilities when there are more than 2 outcomes for each trial in the experiment. That is, the multinomial distribution is a general distribution, and the binomial distribution is a special case of the multinomial distribution. Another type of distribution is the Poisson distribution, a discrete probability distribution that is useful when n is large and P is small, and when the independent variables occur over a period of time. In addition to being used for the stated conditions, the Poisson distribution can be used when a density of items is distributed over a given area or volume, such as the number of plants growing per acre or the number of defects in a given length of videotape. An example of the Poisson distribution is the typographical errors. If there are 200 typographical errors randomly distributed in a 500-page manuscript, find the probability that a given page contains exactly 3 errors. To solve this one, first, find the mean number lambda of errors. Since there are 200 errors distributed over 500 pages, each page has an average of lambda is equal to 200 over 500 is equal to 2 over 5, then the answer is 0.4 or 0.4 error per page. Since x is equal to 3, so substituting in the formula yields probability of x such lambda is equal to e to the power of minus lambda times lambda to the power of x over x factorial is equal to 2.7183 to the power of negative 0.4 times 0.4 to the power of 3 over 3 factorial is equal to 0.0072. Thus, there is less than a 1% chance that any given page will contain exactly 3 errors. Since the mathematics involved in computing Poisson probabilities is somewhat complicated, tables have been compiled for these probabilities. So, in example 527, where x is 3 and lambda is 0.4, the table gives the value 0.0072 for the probability. In continuation to the Poisson distribution, we have another example, which is the toll-free telephone calls. A sales firm receives on average 3 calls per hour on its toll-free number. For any given hour, find the probability that it will receive the following: A, at most 3 calls, B, at least 3 calls, and C, 5 or more calls. Let's solve first the letter A, which is the at most 3 calls. Note for the formula of the Poisson distribution, so probability of x such lambda is equal to E, where E is a constant approximately equal to 2.7183 to the power of minus lambda times lambda to the power of x over x factorial. So, lambda here is the number of occurrences in a particular interval of time. So, our lambda here is 3. And x denote as the number of occurrences or the success. So, our x here are 0, 1, 2, or 3. So, probability of 0 such 3 is equal to 0.0498 plus probability of 1 such 3 is equal to 0.1494 plus probability of 2 such 3 is equal to 0.2240 plus probability of 3 such 3 is equal to 0.2240 is equal to 0.6472. So next is letter B, which is at least 3 calls. It means 3 or more calls. It is easier to find the probability of 0, 1, and 2 calls and then subtract this answer from 1 to get the probability of at least 3 calls. So, probability of 0 such 3 is equal to 0.0498 plus probability of 1 such 3 is equal to 0.1494 plus probability of 2 such 3 is equal to 0.2240 is equal to 0.4232. And 1 minus 0.4232 is equal to 0.5768. For letter C, for the probability of 5 or more calls, it is easier to find the probability of getting 0, 1, 2, 3, or 4 calls and subtract this answer from 1. Hence, probability of 0 such 3 is equal to 0.0498 plus probability of 1 such 3 is equal to 0.1494 plus probability of 2 such 3 is equal to 0.2240 plus probability of 3 such 3 is equal to 0.2240 plus probability of 4 such 3 is equal to 0.1680 is equal to 0.8152. And 1 minus 0.8152 is equal to 0.1848. So that's the answer. Thus, for the events described, the Part A event is most likely to occur and the Part C event is least likely to occur. Since our letter A is 0.6472 while the letter C event is 0.1848. So, another example of the Poisson distribution is the left-handed people. If approximately 2% of the people in a room of 200 people are left-handed, find the probability that exactly 5 people there are left-handed. To solve this one, since lambda is equal to n times p, then lambda is equal to 200 times 0.02 is equal to 4. Hence, probability of x such lambda is equal to 2.7183 to the power of minus 4 times 4, which is the lambda, to the power of 5 over 5 factorial is equal to 0.1563, which is verified by the formula similarly to 0.1579. The difference between the two answers is based on the fact that the Poisson distribution is an approximation and rounding has been used. Next, another type of distribution is the hypergeometric distribution. When sampling is done without replacement, the binomial distribution does not give exact probabilities since the trials are not independent. The smaller the size of the population, the less accurate the binomial probabilities will be. For example, suppose a committee of 4 people is to be selected from 7 women and 5 men. What is the probability that the committee will consist of 3 women and 1 man? To solve this problem, you must find the number of ways a committee of 3 women and 1 man can be selected from 7 women and 5 men. This answer can be found by using combinations. It is combination of 7 and 3 times combination of 5 and 1 is equal to 35 times 5 is equal to 175. Next, find the total number of ways a committee of 4 people can be selected from 12 people. Again, by the use of combinations, the answer is 495. Finally, the probability of getting a committee of 3 women and 1 man from 7 women and 5 men is probability of x is equal to 175 over 495 is equal to 35 over 99. The results of the problem can be generalized by using a special probability distribution called the hypergeometric distribution. The hypergeometric distribution is a distribution of a variable that has 2 outcomes when sampling is done without replacement. The probabilities for the hypergeometric distribution can be calculated by using the formula given next. Note that the formula for the hypergeometric distribution, given a population with only 2 types of objects, females and males, defective and non-defective, successes and failures, and etc., such that there are A items of one kind and B items of another kind, and A plus B equals the total population, the probability of X, selecting without replacement a sample of size n with X items of type A and n minus X items of type B is probability of X is equal to the combination of A and X times combination of B and N minus X over combination of A plus B, which is equal to the total population, and N, which is the number of trials. Also, X here is the number of success in N trials. So the basis of the formula is that there are combination of A and X ways of selecting the first type of items, combination of B and N minus X ways of selecting the second type of items, and combination of A plus B and N ways of selecting N items from the entire population. Another example of hypergeometric distribution is the assistant manager applicants. 10 people apply for a job as assistant manager of a restaurant. 5 have completed college and 5 have not. If the manager selects 3 applicants at random, find the probability that all 3 are college graduates. To solve this one, assign the values to the variables first. It gives A is equal to 5 college graduates, B is equal to 5 non-graduates, N is equal to 3, which is the number of trials, and X is equal to 3, which is the number of success in N trials. And N minus X is equal to 0. Substituting in the formula gives probability of X is equal to combination of 5 and 3 times combination of 5 and 0 over combination of 10 and 3 is equal to 10 over 120 is equal to 1 over 12. Another example of hypergeometric distribution is the house insurance. A recent study found that 2 out of every 10 houses in a neighborhood have no insurance. If 5 houses are selected from 10 houses, find the probability that exactly 1 will be uninsured. In this example, A is equal to 2, B is equal to 8, N is equal to 5, X is equal to 1, and N minus X is equal to 4. Note that N is the number of trials and X is the number of success in N trials. So, substituting in the formula, it gives probability of X is equal to combination of 2 and 1 is equal to 2 times combination of 8 and 4 is equal to 70 over the combination of 10 and 5 is equal to 252. Then the answer is 140 over 252. Then reduce the answer to 5 over 9. A lot of 12 compressor tanks is checked to see whether there are any defective tanks. 3 tanks are checked for leaks. If 1 or more of the 3 is defective, the lot is rejected. Find the probability that the lot will be rejected if there are actually 3 defective tanks in the lot. To solve this problem, since the lot is rejected if at least 1 tank is found to be defective, it is necessary to find the probability that none are defective and subtract this probability from 1. Here, A is equal to 3, B is equal to 9, N is equal to 3, and X is equal to 0. So, probability of X is equal to combination of 3 and 0 times combination of 9 and 3 over combination of 12 and 3 is equal to 1 times 84 over 223. Then the answer is 0.38. Hence, probability at least 1 defective is equal to 1 minus probability of no defective is equal to 1 minus 0.38 is equal to 0.62. There is a 0.62 or 62% probability that the lot will be rejected when 3 of the 12 tanks are defective. Binomial distribution used when there are only 2 outcomes for a fixed number of independent trials and the probability for each success remains the same for each trial. So the next one, the second one is the second one type of discrete distribution is the multinomial distribution. So it's used when the distribution has more than two outcomes. The probabilities for each trial remain constant. Outcomes are independent and there are a fixed number of trials. So the third one is the Poisson distribution, used when n is large and p is small. The independent variable occurs over a period of time, or a density of items is distributed over a given area or volume. So that is a Poisson distribution. So the fourth one, the last one, is the hypergeometric distribution. It is used when there are two outcomes and sampling is done without replacement. Thank you for listening, and I do hope that you've learned and gained something in our lesson today, and that's for today's discussion. I hope you guys have a good day. Thank you.
I know